going to start from 11.3 and hopefully we'll get to 11.5. If I don't finish 11.5, that's okay. Since, you can see from the packet I gave you, it's a super short, and it's all about the formula, okay? Oh, yeah, sure. But the something I want you to first think about and tell me your thoughts. So here, 0.99 repeating, right? It's a infinitesimal. Do you think that's the same as 1? Raise your hand if you think they are the same. No one. Because they look very different, right? But raise your hand if you think they are different. Please let me know. Okay, most of you. Okay. And you'll see how to deal with that, or are they the same or not after you learn the geometric sequence. Okay. But have you guys heard of geometric sequence in the past? Geometric sequence and series. But what about arithmetic? You learned it before, probably in algebra 1 or 2, right? So typically the geometric series, so I keep saying geometric series because in calculus they have the series. So the geometric sequence come together with the arithmetic sequence. Anyway, so we'll come back to that question once we pretty much done with 11.3. Let's dim the light a little bit. All right, so once again, start from the definition. I guess that the word geometric or arithmetic, didn't really tell us anything. But if you're looking at an example of a classic geometric sequence, so you start from 1 and to get to the next term. So you do something to get to -2, right? So you might thought that, am I subtracting 3? Well, then you realize to go from -2 to the third term, +4, I hope that you start to see some pattern behind it, right? Then go from 4 to -8, right? So what do you see that's happening here? What's the pattern? Donovan? So every time you multiply a -2, right, to go from a term to the next one. So now at this point, until the end of this lesson, so I want you to keep thinking about the arithmetic sequence, because you're going to see those formulas which are closely comparable to the formulas you have for the arithmetic sequence. Okay. Now remember what that little d stands for in arithmetic sequence. Lowercase d, which stands for, anyone remember? Say it again. No, lowercase d. Common difference, right? D stands for difference. And now since we keep adding, right, or subtracting that common difference, right, to go from a term to the next one. But when it comes to geometric sequence, we keep multiplying or could be dividing a common ratio to go from a term to the next one. Here, the common ratio is -2. So you multiply 1 with -2, you get -2. Multiply one more time, you get 4. Then one more time, you get -8. Therefore, you'd find the ratio of 2 consecutive terms in a geometric series, a sequence. It will be a constant, and that's why we call it common ratio. And the order does matter as well, just like the arithmetic sequence. So you're going to take the term divided by its preceding term. Okay, so it's always a sub 2 divided by a sub 1, or a sub 3 divided by a sub 2, right? And that's our definition. So make sure that you do the correct order to find the common ratio. Okay. Now let's compare that with now, not writing down things that for the geometric series on the side, right? So I'm telling you that if this is how we define a common ratio for geometric series, how do we define the common difference for arithmetic sequence? Something about a sub n minus 1. Anyone recall that? Would be a sub n minus a sub n minus 1 is d, right? See that? This is common difference, where here we have common ratio. Okay? Now, we went from the definition of a common difference into the definition of the recursion formula, right, for the arithmetic sequence. So you see that we can do the same thing, right? Just by rewriting this equation by multiplying both sides by a sub n minus 1. So we're looking at a sub n minus 1 times the common ratio to get you the a sub n, right? And you can do it recursively. Every time multiply the common ratio, you get the term right after it. Compared to the similar thing, right? So a sub n is a sub n minus 1 plus the common difference. Okay? All right. Now, this is when things, again, gets a little bit confusing. You know, it happened in the common, in the arithmetic sequence. Since we're always multiplying, as for now, right? So there we'll divide. But right now, let's say always multiplying a common ratio to get a term, right, to the next one. So if I'm going to start from a sub 1, okay, does it make sense that we're only multiplying the common ratio for not n times, but n minus 1 times to get to a sub n? And it's like we're adding not n times of the common difference, but n minus 1 times common difference to a sub 1 to get a sub n back in the day, right? Do you see that they are super comparable? And also, if you've been a big fan of the general form of that kind of an nth term formula, right, in 11.2, the one that has m in it, do you see that? If it were arithmetic, you're going to start from anywhere in a sequence. Let's say a sub m, right? You're going to add n minus m times common difference c to the a sub m to get a sub n. The same thing here, right? Keep multiplying the common ratio, but only for that many times. And the number of times of the common difference, or the number of times of the common ratio, this is actually the power, right? When I say multiply for that many times, it's actually raising the common ratio to the power. That's the difference between the two indices. Okay? Now, let me pause for, a brief moment. How should you memorize, right? Well, of course, you have notes for the quiz, right? In a test, how would you be able to memorize these things? Not everything, because I sense that, most people are going to choose to memorize this one, right? Instead of, the one that's sort of a sub n, right? But you do have the one for geometric, right? For arithmetic, right? And also the recursion relation, right? Do you see that? You should never treat it as doubling the work. It's not, right? Intellectually, they are the same. And I want you to take the analogy, right? If you're a big fan of geometric, I don't think most likely that's the case, right? People are thinking about addition, subtraction, more intuitive. Go with the arithmetic. Then quickly write down the corresponding version involving common ratio, right? And it's not addition anymore, it's multiplication, right? But do you see that the number of terms, right? The number of times of the d, number of times of the r are the same. All right, so now let's, we'll get to the grade, right? So I didn't forget, I was looking at the time. So let's work out a few problems before you take the break, right? Letter A. We're given a sub 1, right? A common ratio -2, right? So let's find out the 8th term. And I guess that would use the first version, right? So take the n to be 8. So a sub 8 is a sub 1, right? Times r to the power of 8 minus 1, right? Notice that's always a difference between the indices. That'll be negative 4 raised to the power, oh, my bad. Negative 4 is just the a1, right? Times, no, negative 2, which is the common ratio, raised to the power of 7. All right. So I'm sure that you will have to use calculator for most of the calculations in arithmetic. You can do mental math, but you know, are you gonna remember how much is 2 to the 7th, right? So now once you guys type it up real quick and tell me what you get. Negative 4 times negative 2 to the 7th power. $512, right? 512. So make sure that everyone gets 512. It's positive, right? Since you're raising a negative number to the odd number, it's a negative number multiplied by another negative number. It has to be positive. Good. Now let's do letter B. We want the explicit formula. Do you still remember that in the arithmetic sequence, the explicit formula is about a sub n, right? It has the n explicit there, so it's ready to go. Whenever you plug in any number for n, it will get you that particular term. And we want the same thing, right? So we're looking for what a sub n is. Okay. So now you can take a look at the formula, right? Whichever you want to use. I suggest that you use the one that has m in it, since you do have a sub 2, a sub 5, right? Save you some trouble. Do not find a sub 1 because, you know, it's not necessary. Start from a sub 2, right? But the problem is we still need the common ratio. How do we find a common ratio given two terms? And also we know exactly where those two terms, you know, located. It's the second and the fifth term, okay? But I guess that, you know, it's not hard to, you know, imagine what you should do, but algebraically, it might not be as straightforward as the, you know, arithmetic version. So let me write it down, right? So I'm going to be looking at the formula a sub n equals to a sub m times r to the n minus n power, right? Where I'm going to take n to be, say, 5, and to be 2, okay? So that means I'm looking at a sub 5, right, is a sub 2 times r to the power 5 minus 2, so will be 3, right? So that translates into a numerical equation about r. So a sub 5 is negative 1/3 equals a sub 2, that is 9, times the common ratio, which is what you're looking for, raised to the third power. So now I want you to solve for r. You guys do that. Go ahead, work it out. What is r? Negative 1/3, right? So what'd you do? That's okay. Okay. So you see that it's, you know, 1/3, right? So or you divide by 3 for that many times, you happen to get, you know, either a sub 9 or stuff like that, right? That's fine. I'll say that, you know, if you want to be safe, right? Sometimes, you know, maybe the common ratio is not going to be a nice number, right? So what I will do, again, you know, if it's a, you know, FRQ, you're going to divide both sides by 9, right? So that becomes, so now remember that the key change flip thing, right? Or, you know, just type it up in the calculator. It'll be negative 1/27 equals r to the third, right? So then what you do is taking the cube root, right? And you're going to get negative 1/3. Okay, or let's put cube root of -1/27, right? It will be -1/3. Right? Is that okay for you guys? Okay. And that's the common ratio, right? So now once you have the common ratio, so how are you going to get the, well, you know what? Let me get those things a bit to the side. So you have the absolute freedom to take whatever number you want. But in this case, the reason why I'm taking the n and m, oh, sorry, there's a typo. It's m, right? Hopefully that's not the thing that confused you. So the reason why I'm taking n and m to be 5 and 2 is those are the two terms they provide us. Sure, yeah. And if you do that, you get the same thing, right? But you have to be careful with the order, right? If you say that you're gonna take here, like a sub 2, right, equals a sub 5, then make sure you plug in the correct number, right? But yeah, like I said, the n and the m, either in the geometric formula or the arithmetic formula, they don't have to be, the number you thought they have to be, right? So let's say m is not always necessarily less than m or greater than m. It could be anything. You know what? You can even set them to be the same. You're going to get trivial answers, right? Now, to get the a sub n, like I said, you should be flexible with where the starting point is. So how about we start from a sub 2? Right? So now you're going to have to multiply the common ratio, right, up to n minus 2 times. That's raising the common ratio to the power of n minus 2, right? So that tells me a sub 2 is 9 times common ratio is -1/3, okay, to the power of n minus 2, okay? Now, you could seriously leave it like that. That's a FRQ. Nothing wrong with it, right? But if you want to get something to the perfection, or maybe you're worried about the options in the multiple choices doesn't look exactly like that, you could simplify it, right? And all I have to do is, recall their property of exponential expressions, right? So you can separate the power, and it goes like -1/3 to the nth power times, right? -1/3 to the power of -2, right? When you multiply the same base to the different power, you get to add up the power, right? But now I'll go backwards, right? Splitting the power. Well, you should be able to calculate what -1/3 to the -2 is, right? Now, if you want to do mental math, the negative power is going to turn that into its reciprocal, right? So this is basically -3 to the second power. Then you square, right? -3, you get +9. 9 times 9 is 81, right? So 81 times -1/3 to the power n, okay? If that's what you want. But maybe some of our students decide to overkill it. They say, you know what? This is nothing but -27 to the nth power. Is that right? Is the last line correct algebraically? Why not? In what way? Well, do you see what the student did? It's 81 times -1/3. Isn't that -27? I think it is, right? Then what's wrong with that? Okay, so the exponent goes before the multiplication. So you cannot do that, right? So I'll be generous enough when it comes to the FRQ. If you do that, hopefully I pretend I didn't see it. But hopefully you had the first line correctly, so I feel like that. Say it again. What do you mean by 1%? Oh yeah. So if you want to do that, that's fine. So, but yeah, if the algebraically, what you told me is correct, but not this guy, right? But this could be one of those options in multiple choice, right? Those guys know that many common mistakes. So please, all right, be careful with that. All right, so I think that's good enough for our first session today. Sorry, I was keep you a little bit longer, right? I want you to take, if you don't mind, let's take a little shorter break. I do want to get to the stuff I planned, right? So how about maybe 5 minutes? Just quickly do some stretch and go to the restroom if you want, right? Yeah, let's come back in 5 minutes. All right. 5 minutes countdown. Yeah, how many? Say it again. Oh, the 0.3 is on the back of the 0.2. Yeah, well, take a look at the packet. Yeah, I staple because arithmetic and geometric are usually. Oh, you didn't bring it? Yeah, so take a look because I think that they're together. S5. Okay, so let's say you want to do the other way around. Okay. Oh, we don't need to, since the explicit formula is what a sub n is. So that means I leave the n as is. I just going to specify the explicit term that I'm going to start with. So it's like doing the same thing again, but without specifying what the n is, only specify what the m is. Yeah, that's right. And also we have the n left over. Right, we do need that n because that's what makes the formula explicit. Yeah. Oh, just in case, if you didn't know, so in the summer, if you have to be absent for a certain day or days, you need to get approval from Miss Hager to be able to get you the makeup. All right, so that means if you have to be gone, and that happened to be the day that I have either a quiz or anything that worth the grade that you missed it. So I'm not allowed to give you a makeup right away without her permission. It's just for summer, right? So therefore, I think that now there are a few people are sending out emails, CC the instructors, right? They email Ms. Hagen, and so basically, for makeup, if you're absent, then I need to get the approval from her in writing before I can give you that, right? Or the worst case scenario is you just take that, missing grade, right? Just so you know, right? Nothing crazy. It's just that since it's only 23 days, so you can still reach out, let us know. It's just that the makeup is not automatic. Yeah, there's a detailed policy. Yeah, so I think that within 1 day, so I think that maybe instructor has a little bit of freedom to, look into that. But I'll say that just be safe. I'll even reach out to Ms. Hager and say, hey, the student has missed 1 day, right? And have to be, quiz, right? So what should I do, right? Yeah. All right. Oh yeah, we have. So let's wait for just 1 more minute. And what I'm gonna do in a second is to work out that question that I raised at the beginning of the class. That is 0.9 repeating the same as 1? And once you see that visually with a explicit example, you will see that trick. Whoever came up with this way, it's just so brilliant. So that's going to help us to sum up however many terms from a geometric sequence. But I guess that it's a little bit hard to track, what's going on, since they're having so many symbols and they're, infinite many terms, right? So therefore, it's better to look at a particular example to experience, how that trick works out. Okay. At the same time, I think that question could seem like a little bit philosophical, right? And for those who be taking calculus in the fall, so I think that soon you'll realize maybe the first chapter in calculus, they will through the concept called the limit. To me, I mean, so now it's fine, and I start to appreciate the concept of limit. But I think that it was, it's just, super counterintuitive when it comes to the limit, right? So it's very similar to what you're going to see in that example. Okay? And also on the packet 11.3, on the very back, there was a very famous paradox. Do you guys know what paradox is? You understand what it means? Have you heard of that word, paradox? Okay. So here's one. Let's say that's a famous one, it's called the barber shop paradox. So this guy is the only barber in the town, and he decided to only cut the hair of those people who can not cut their hair on their own. So does it sound right? So he said that he's going to cut anyone who couldn't cut their hair on their own. And he's the only barber in town. Sounds fine, right? But what about he decided to cut his hair on his own? Is he allowed to do that? will he break his own rule? Because if he did decide to cut his own hair, he shouldn't, because he only gonna cut the hair for those people who cannot cut their hair, on his own, right? But if he chooses not to, then he should have. Do you see the problem? Logically, it's just a flaw, right? So this is called a paradox. So something that sounds reasonable, but it's wrong. Okay, but a lot of the science, subjects, that paradox are usually things that people thought is true before they understand the theory good enough. And sometimes people try to pose, paradox to disprove something because they don't want to believe in it, right? But later on, once we understand the theory enough, a paradox or a trend, can be proved to be false. And this is actually one of the famous paradox. So it's, got a name of it. I think it's either, because it's the Greek guy, Kino or Kino. So this Greek guy, those people are what we call philosophers back then, right? So those are just smart people. So he figured that, you guys know the Greek hero, what's his name? Precalculus, right? So they say this guy, super fast, right? So he's gonna go from point A to point B, and the distance between these 2 points is only 1 meter. Let's say, I'm trying to walk from here to just 1 meter far. What do I have to do? He said that you have to get to the midpoint. That means I have to go first half the meter, right? So now, to get to, the destination, I have another half meter to go. But he said that to get to the next half meter, you have to get to the half of the next half meter, which is going to be a fourth, right? So now to get to the remaining fourth, to get to the half of the remaining fourth, which is 1/8. You keep going. So now, do you see that? You have to take infinite many steps. Each step gets halved, right? It gets smaller, but it seems that you'll never make infinite many steps, right? Unless you wait infinite long. Does it mean that you will never get to the point B, even if it's just 1 meter far? Then the question is, would you get there or not? But it just doesn't make sense. You can definitely get to point B. It's only 1 meter far. And that's why it's a paradox. But that paradox can be solved. And it's wrong because you will get to the point B, and all you have to know is the geometric series or geometric sequence, right? Anyway, so since everybody's here, right? You know what? Let me still get started because I do have to finish at least 11.3. Hopefully, I'll get you started with maybe some reading of 11.5. All right, so let's get to this question. Now, here's something we could do just to massage that, weird, decimal, right, 0.9. All right, so consider let's say S is 0.9999 ... Okay. Now let me multiply this number by 10. You guys tell me, how much do I get if I multiply 0.99 repeating by 10? So just get 10 times bigger, right? Does everyone agree that you're going to get 9.9999 ... right? We good? All right, so now let's say this is equation number 2. That's equation number 1, right? So let's subtract equation 1 from equation 2, right? So to do that, on the left-hand side, it will be 10s minus s. On the right hand side, you get 9.9999 dot dot dot, right? Minus 0.9999. But what do you get on the left hand side? 10s minus s is 9s, right? It's like 10x minus x, right? So 9s, 9 times s. Now what about the right hand side? What do you get? 9. All the decimal places are gone, right? Then last time I checked, s has to be 1. So what does it mean? It means that 0.99 repeating is 1. So that means you always think that you have a tiny bit difference away from 1, right? But what is that little difference? Is it 0.1? No, 10 times smaller or 10 times smaller, right? So whatever distance you think you're away from 1, I can always come up with a difference that's smaller than whatever you told me, right? But that never ends. So now I'll say in a for, you see that in the sense of the limit, 0.99 repeating is 1. So you see that this number is infinitely close to 1. It approaches 1, right? But is it ever 1? I mean, what do you think? It's probably never 1, but it's so close to 1, right? So maybe it's 1 at the end, right? Or close enough to be 1, right? So, I mean, it seems that you never had to run at all because it is 1. So this is like when I take that trip, right, from point A to point B, it's a meter far. I first take a half meter, then I take a fourth, then an eighth, right? So when I add up all that many steps, so eventually, if I do wait long enough, I will eventually get to 1. We add up 1/2, 1/4, 1/8, right? 1/16, 1/32, the 32nd, it's going to be 1. But in physics, the space, the time, or anything is not infinitely divisible, right? So think about this. Is it possible for you to make a step that's infinitely small? You can't. You cannot, right? Because the smallest size you can never think of in the physical world is probably as small as an atom, right? Maybe as smaller as an electron, a quark, right? We don't know anything that's smaller than quark. So that means you're not going to be able to get to, like infinite small distance, right? So for example, like, I have a pen, which is 10 centimeters. Every day I cut it in half, right? Then I cut it in half and a half. Will I eventually be able to do that forever? No, at the end of the day, I get to the quark, right? I get to the atom, the electron. That means the space, the matter, the time is not infinitely divisible. So at the end of the day, there's going to be a moment that you take the final step, however small it is, it will take you to the point B, right? So, but that's how mathematicians and scientists are thinking. Sometimes a little bit different, right? Anyway, so keep that in mind. That little trick, which is kind of brilliant. And I didn't came up with that, but that's actually exactly what they did over here, right? So now again, I'm not going to get too crazy about this generic proof, right? So at the end of the day, you just need to know how to sum up, right, the geometric series, a sequence, by the way. So let's take a look at the S sub n, right? So the subscript n stands for however many terms that you want to add up from a sequence, right? Say take the n to be 100, you're going to add up the first 100 terms, right? And by the way, we do have a name for it. It's called the nth partial sum. And I hope you realize that the reason why they call it a partial sum is that the sequence, it has infinite many terms. You're only adding the first n terms, it's partial. Okay. Now, how do you write out the first n terms, right? If it's a geometric sequence, start from a sub 1, right? That's the first term. How do you get to the next term? Multiply r, right? Then multiply r one more time. Keep doing it, right? Now, here's something I always try to check, to make sure that you get it. Do we have exactly n terms? Or do we have actually n minus 1 terms? Over here. Start from a sub 1 all the way to the last term that seems to be the form of a sub 1 times r to the n minus 1 power. Is it n terms or n minus 1 terms? It is n plus 1. All right. So see that usually we're off, right, by 1, either n plus 1, n minus 1, or n. But in this case, it is n terms. There are many ways to see it. First off, you see that this is exactly what the nth term formula looked like, right? That means you go from a sub 1 to a sub n. I just didn't write it as a sub n. That's one way to see it. Another way to see it is, hey, what if n is 1? A1 times r to the 1 minus 1, r to the 1 minus 1, r to the 0 is 1, right? That means the last term becomes the first term if you were to take n to be 1. That's how you count, right? N to be 1, that's the first term, all the way to n, but that's the n term. So either way, so you need to be able to count it correctly, because if you're off, you're off by 1 term, but that's still wrong. So this is still the first n term, right? So now remember what that little trick worked out for the 0.9 thing, right? So you multiply something, right? So you multiply, in this case, the common ratio. But did we actually multiply the common ratio? Go back. So I multiply the 10. So is the 10 a common ratio? What do you think? So you can see that by thinking about how would you write 0.99 repeating, right? So isn't that 0.9 plus 0.09 plus 0.009 ... right? So now, what's the ratio between two terms? Say 0.9 divided by 0.09, or the other way around. What do you get? Either 10 or 1/10, right? So now if you don't like 1/10, flip it over. Start from the very end, right? So the number is going to be 0.00009, right? Then 1 let 0 all the way down to, well, 0.9, right? So either way, you see that it is a common ratio, or the worst case scenario, it's the reciprocal of it, right? But anyway, let's take a look at what they did with the common ratio. And you'll see that some kind of a magical process just by multiplying a common ratio. So you're going to do that for every single term on the right-hand side, right there, right? The first term gets a sub 1 times r. Second term is a sub 1 times r squared, and so forth. Now, do you realize that it was r to the n minus 1 power at the end, right? But once you multiply a r, it changed that power from n minus 1 to n, right? Okay, so now let's subtract the second equation from the first equation, right? On the left-hand side, it's this guy minus that, right? So you take s sub n minus r times s sub n. But I don't know if you can see that, but just take a close look. If you write the if you write the sum from A1 all the way to A1 times R to the n minus 1, right on top of A1 times R to R squared. As you subtract them, do you see that there are so many terms get canceled, right? And you're left with, remember that you're subtracting equation 2 from equation 1, right? See that A1 times R, it canceled by A1 times R because you're subtracting them, right? So most of the terms are gone except for the first term, that is A sub 1, and the last term is A sub 1 times R to the n. And therefore, that's what you get on the left-hand side, right? S sub n minus R times S sub n. And the right-hand side, just by subtracting those many terms explicitly, you get most of the terms are gone, right? It's just the first two terms, first and last term. So now what you can do is solving for S sub n, right? I guess that you can factor out, what S sub n is, right? So you get 1 minus R, right? I don't know if you see that. So maybe I'll just put in one more step, right? So you're factoring the S sub n, so you're gonna get S sub n, right? Factored out 1 minus R, right? And that's equal to A sub n minus A sub 1, sorry, A sub 1 minus A sub 1 times R to the n, divide out 1 minus R, and there you get the summation formula for the nth partial sum of a geometric sequence. And it takes A sub 1, right, the starting point, the first term, and the common ratio, and it's raised to the power n. But it looks a lot more complicated than the Gauss's formula, right, for the arithmetic sequence, right? Not to mention, we have the powers, we have the divisions, right? Or sometimes, people might mess up the order, right? So they thought that it's R to the n minus 1, right? But in this case, it's actually 1 minus R to the n divided by 1 minus R, okay? And things could be kind of ugly, if you do this kind of division, right? Not to mention that when terms gets, a lot more than what you normally deal with, and if the common ratio is, kind of big, you might get a large number, right? Easily beyond what the calculator can deal with, okay? But here's a little subtlety that a common ratio cannot be 1. Not that I say that when the common ratio is 1, you don't get a geometric series. Sorry, I keep saying geometric series. You don't get a geometric sequence. So what if the common ratio is 1? Can you guys imagine a geometric sequence that has exactly 1 as its common ratio? Start from A sub 1, right? So what will be the next term? Its common ratio is 1. Would you say it's still A sub 1, right? Because always multiply the common ratio, you get all the terms, right, in the sequence, they're all the same. So now what if you have, n terms? So you sum up, right, the first n terms, and you're going to get n times A sub 1, right, if common ratio is 1. That means it's a trivial case. So you know how to sum up all that many terms if you get a common ratio to be 1. But if it's not 1, unfortunately, you have to do that formula. But at least that you have something to work with. Right? Let's try letter A here. Let's find out the sum of the first 16 terms. All right, so now S sub 16, right? So you're going to need A sub 1 times 1 minus the common ratio. Now, can anyone tell me what will be the common ratio for this geometric sequence? Start from 2, then -8, 30, So negative 4, right? So now let's make sure that we are taking negative 4 to the power of 16, right? Because that's the n, right? However many terms you're going to add up, divided by 1 minus negative 4. Do you see that I'm getting paranoid with the parentheses? Because I want to make sure that you do make sure that the sign is correct. You are subtracting a negative common ratio. Okay? Oh, sorry. The a sub 1 should have been just 2, right? And of course, type it up in the calculator, right? And you're going to get, see what you get. Wow. That's, do that in your calculator. Let me know how you're going to read that number. How do you read it? It's a big number, basically. Right? So, but you see that how many terms did we add up? Only 16 terms. Yeah, that's how quickly the geometric, sequence will grow. I mean, absolute value, right? Yeah, so I mean, I guess that now's a good time to use scientific notation, right? But anyway, all right. So now, calculator time. All right. So why don't you first find out what letter B is? It's a summation notation. Type it out correctly. Get the answer, and then we're gonna work it out algebraically, just like the arithmetic sequence. All right. So go ahead. But I hope that you realize that it is a geometric sequence. And you can also identify the common ratio and a sub 1, but you don't need that if you just have to figure it out, the summation notation using the calculator. Actually, now I'm actually pretty confident. I saw, how quickly you guys were in the quiz, right? So you guys all get that? Yeah. That's 12,276. But now let's see how to get that algebraically. So I know that I need to add up the first 10 terms, right? That means I need a sub 10, right? So that will be a sub 1 times 1 minus r to the 10th power divided by 1 minus r, right? Now, what is a sub 1? I mean, this is the generic term, right? It's a sub I. So when I becomes 1, that's the first term, right? So it'll be 6 times 2 to the first power, so it'll be 12, right? But you guys tell me what a common ratio is. How do you find it? It's 2, right? Jordan, can you tell us that, what makes you think that it just looks like a 2 common ratio? Okay, so it's the base, right? It's the base of the exponential expression. So does it make sense that as you running the index I from 1 to 2 to 3 to 4, you're basically getting the 2 to the power, right? Like every time you increase the index by 1, you're going to multiply a 2. So that means that the base of the exponential expression is the common ratio, right? But of course, if you want to be safe, get what a sub 2 is, right? What is a sub 2? 6 times 2 squared, which is 24, right? Divide and get yourself the common ratio, right? Which is a2 over a1. If you know it's geometric, most likely, it will tell you, right? But, not always. Because now we have everything, right? So s sub 10 is, a sub 1, that is 12, right? Times 1 minus 2 to the 10th over 1 minus 2, and you do get the same thing. Okay. But I guess that getting the answer is never going to be an issue for summation notation, right? But just make sure that you're able to show me work like that in the test for a FRQ. Okay. Now, any questions so far? Am I going too fast? But hopefully that you are comparing the arithmetic and the geometric. So find things that are similar enough, right? So you don't have to memorize twice again. But for something that's a little bit different, like the formula for the nth partial sum, then find a way to remember. Okay. So now let's see that. What is that thing that I keep saying, right? The geometric series. So it is a little bit different from geometric sequence. So if you remember, I defined the sequence for you back in 11.1. I said that sequence is a list of numbers, right? But now, what if you want to add them up? So once you add up all the terms in a sequence, that sum, which is obviously an infinite sum, right? A sum of infinite numbers, that sum has a name, which is called a series. Now here's the funny thing that, I hate to say the word series because whenever I say it, but this time it didn't respond, right? So maybe it's because me pronouncing it in a way that's not as native as supposed to be, right? It's so awkward when I tutor, then when I say series, then it's gonna respond, right? Anyway, but hopefully you remember that when you put down something, when it comes to geometric sequence of series, it will be a very different thing, right? So series is a fancy way to say add up all the terms in a geometric sequence, right? But sequence is a list of numbers. So now you're looking at the infinite sum, right? The sum of everything in the geometric sequence, starting from a sub 1 all the way to however many terms, right, you want. How do we get that, right? Since that seems a bit scary, right, to add up all that many terms because it has infinite many terms. And it turns out that it is as easy as it seems. Basically just make the nth partial sum formula where the n is, make it as large as you can. Just make it infinite. But the thing is, there's no way you can type in infinite in a calculator, right? But you know what? Do you see how quickly the geometric sequence grow or decay? Even just by counting 16 terms. So how many terms do you think that, relatively speaking, will be enough to be considered as infinite? You might think maybe it take 1 trillion terms, right? You don't have to do that. Sometimes 50 terms is good enough. If you want to be safe, do 100 terms. If you do like a 10,000, like a million, your calculator is probably not gonna be able to do it, right? But just big enough, right? A real number, 1,000 terms, right? That will be big enough. All right, so now let's actually see, if you're gonna get that formula anyway, if you just do it, right? So of course, later on, you're gonna appreciate that formula for adding up infinite many terms in a geometric, let's say, sequence, right? Yeah, one. Let's see. right? So that's what I'm going to do in letter A. So we're going to add up all the terms in the geometric sequence, start from a sub 1, which is 3, right? So let's say if I were to add up the first n term, oops, what does it look like? So a sub 1, right, times 1 minus r to the n over 1 minus r. So what is a sub 1? 3, right? What about a common ratio? In this case, it's what? A sub 2, maybe a sub 1. You'll say it would be just 2/3, right? Now, I mean, it's absolutely fine to get either a decimal or a fraction, right? Irrational number to be a common ratio because it's a real number. You're going to raise that to the power n divided by 1 minus 2 to the third. Okay. So of course, I need to figure it out, right? Let's say n is as big as I want it to be. But I said that, you know what? Take the n to be 100. That's probably good enough, right? So let's try that, right? Let's type it out in the calculator. But you know what? I like the decimals at this point, since it's, a little bit better, right, when it comes to interface. So 1 minus 2 over 3 to the n. Okay, let's see. And I like the scientific version, just so you know. All right, so I need the fraction, right, that has 3 on the top, right, times 1 minus 2/3, right, raised to the power of something, right? So let's say, maybe, let's try some small numbers, right, to start with. 1 minus 2/3. Okay, so now, that's, 8 point something, right? So what about 20, 50, 100? Oh, well. Okay, 100, it turns out to be 9. 1,000, 10,000. Right, decimals, your calculus is probably not going to do that. Let's see if it's going to blow up. You know what? It didn't blow up because it didn't even bother to calculate. You thought that so whatever's behind the scenes is going to do that many power. He said, no, stop that because you're going to get 9 no matter what. You see that it becomes 9 at a much earlier stage. So let's see. Oh, wow. You know what? Let's try maybe 80. I'm sorry. 60, 50. What did I say? 50 is probably is good enough. So now what do you do if you really want to add up that many terms? If you do get an answer from a calculator, do you really type in infinity to make the n to be infinite? Well, if there's a way to do that, maybe you could try, right? There's not a way to do it. Just make the number reasonably enough. When would you know that's not reasonable? Your calculator is going to complain. That's the error, right? It's not that I say that's wrong, right? You see that decimals can take maybe 10 to the power of 1,000, maybe, right? But not your calculator. But still, that's not as pretty as that formula. All right, so let's see that. What's happening here? They say if you want the nth term to be the sum of infinite many terms, that means you're going to make the n to be as big as you want. But what happened to the r to the n when r is a small number? You saw that it was 2/3, right? It's a small number, less than 1, right? So can you imagine when you're taking a number that's smaller than 1 to a higher and a higher power? What happened? It's going to get smaller and smaller, right? So you take a number that's smaller than 1 to the infinite power. That number becomes infinitely small. And that number can be considered as infinite small will be 0. That means the term get dropped. All you have to do is just to take the first term over 1 minus common ratio. Isn't that easier? Because I guess that sometimes you can do even mental math, right? No need to calculate anymore. But this is only working when the R is a small number. What I mean by small is it's not necessarily positive. The absolute value, that has to be less than 1. But some people say that, what about 1? What if R is 1? Is that small enough? Turns out that it's not small enough for a geometric sequence. It will blow up. It will become infinite if it's 1. Because thinking about this, you're adding however small that number is, say 0.5. You have infinite many 0.5 added up to be infinite, right? But if you have 0.5, right? 0.05, right? Whatever that is, right? So it gets smaller and smaller, right? The common ratio is less than 1. If you add up the infinite many terms, it will be a finite sum. Okay. Anyway, so I hope that you're not going to do this for the infinite sum of the geometric, series, right? You're just going to go with the first term over 1 minus common ratio, which is 3, right? Over 1 minus the common ratio, which is 2/3. How much is 1 minus 2/3? 1/3. How much is 1 over 1/3? Or 3 over 1/3? It is 9. See that could be that quick, right? If you were to use the correct formula. But do you know the difference between the first and the second one? First one gets you the sum of the first n term. But you need to specify how many terms you want, right? What the n is, 100, right? 5,000. This is going to be the infinite many terms, all added up. So you add up everything, okay? Now, let's say back to elementary school. I don't know if it's going to be elementary school or middle school. What was the first time your teacher introduced you the rational number? Eighth grade, 5th grade. Okay. Did they define a rational number for you? Like, what does it mean, a rational number? Or is 0.7 repeating a rational number? All right. I'm glad that SAT don't ask those questions anymore. All right. But I remember I was joking around all the time, in the fall semester. I said, in the fall we had college algebra, right? But when I was in my former high school, I teach the course is called the math for college algebra. It's not college algebra. It's the math you need to be able to do to get you ready for college algebra, right? And what kind of math? The first chapter is numbers, right? I need to tell them what's even number, what's odd number, right? What's rational. What they freak out when they see radicals, right? Even though they have the calculator, right? So don't get me started on that. Anyway, so rational number, if you go look it up, it's called basically, well, it's fraction. If you can write any number as a fraction, it is rational. But now in this case, can we write 0.7 repeating as a fraction? If you could, it is rational, right? So let's see what it means. 0.7 repeating is nothing but 0.7 plus 0.07 plus 0.007 and so forth, right? You see that you can write it as a geometric series. Now, if you were to add them up, what will be your first term? 0.7 over 1 minus common ratio. You tell me what is common ratio. Oh, it decreased by 10 times, right? Would you say it's 1/10 or 0.1, right? However you like, right? So, I like 0.1. Or you know what? Let's go with 1/10. So you get 0.7, and I believe that on the bottom is 0.9, right? And guess what? It's 7/9. Check it out in the calculator. Type in 7/9. See if you do get 0.7 repeating. And it must give you 0.7 repeating, right? Yeah. Well, because it has to round up, right, at the end, because it doesn't show you the. But some calculators now show a bar on the 7, right? Anyway, so that means 0.7 repeating is rational, right? So now I guess I'm gonna hear what you guys think about the dichotomy paradox, which is on the very end of the packet, right? So it's not for extra credits. Don't ask me for something like that. It's something that you want to think, because now you should be able to answer that question. Would you be able to, or convince your parents, right, or your little sibling, right? Can you actually go from A to B just by moving a meter, right? Yeah, of course, right? But what if you do that way? Would you still get to the B or not, point B or not, right? And show them the math, right? Convince them with a calculator, because you know the answer, right? Because this guy will eventually get to the point B. But I want you to see it in a geometric series kind of sense.